All right, well, hello all, welcome. So, we were pursuing the story of symmetric encryption, which is the primitive whose goal is to provide data privacy under a shared key. So you take a message, and under that key you turn the message into a ciphertext, which is supposed to tell you nothing about the underlying message. And the interesting part of the story is that classical ways of doing this, such as substitution ciphers or just a plain use of block ciphers, we discover don't actually work. They don't give us the degree of privacy that we'd like. And that's for a very fundamental reason, which is that they're deterministic, in the sense that once you fix a key and message, there's a unique ciphertext that's produced. And that by itself is enough to give rise to attacks that we care about in applications. And so we came to this shift which said that we actually have to have the encryption algorithm toss coins or make random choices in every invocation, and those choices have to be fresh. So then we thought about how we might do this, and there are a few canonical ways, and all of them use either a block cipher or function family, and so they're usually called modes. And the first one is cipher block chaining. So what it does is it parses the message into blocks and then runs a block cipher where this initial vector is chosen at random, freshly and differently every time for every encryption, and added into here. And then you apply your block cipher, and that chains down. And somewhat simpler in a way is counter mode. Again, there is a random choice. You use that to create a sequence of values, and then you encipher each of them with your function family to create a pad. And then you just XOR the message with the pad. So these are, between them, cover pretty much how encryption is done. So now that we have these schemes, we'd like to know whether they work or not. And we went through that at a kind of intuitive level, and what we found is that from the point of view of protecting attacks, they do seem to do better than prior schemes. But that's not really good enough, because maybe there's some attack we haven't considered yet. So if you want to get a better estimate of security, we first, as we have for many things, need to go back and ask ourselves, how do we plan to measure security? Because our prior metrics are not going to work. It's no longer about pseudorandom function security or even key recovery, because the bad schemes we saw kind of have properties like that. So going back to basics, we're looking at a sender having encrypted some sequence of messages under a key shared with the receiver using some known encryption algorithm. And this indicates that that might have been randomized. And your adversary sees the ciphertext and may even know a little bit about the messages. So we ask ourselves, what kind of things, if it does, would we be unhappy about? The most obvious is that it finds the key. So there's nothing good about it finding the key. However, our realization is that there are other things that are also bad. The first of those is that even though it doesn't find the key, it manages to reverse the encryption on one ciphertext and recover the message. So clearly that's a problem. But when we go further, we see there are all kinds of other things that we should consider problematic. For example, what if it figures out whether the first and second messages were equal without actually knowing their values? We already saw in the voting example that that's exactly what gives away information. What if it figures out one bit of a message? You might say, well, one bit doesn't matter, but maybe it does. Maybe that's exactly what carries, for example, a vote. What if it even figures out some function of bits of different messages? Why should we not want to hide that? There's no reason it shouldn't be hidden. So eventually we come to realize that we kind of want to hide everything about the message. At this point, though, we do agree to give up on one thing. We won't hide the length of the message. It's a string of some length which can vary, and the ciphertext will typically reveal that length. That's not because we are happy that we reveal the length, but because pragmatically it's rather hard to avoid. So barring length, we'd like to hide everything, but then we have to say what that means. So we don't want to do this in some kind of long list, but in some simple, concise metric. And we'll call that a kind of master property, something that's easy enough to specify with games. We have a way to evaluate whether schemes meet it or not. And it should be powerful in the sense that it should imply all the types of security conditions we saw previously, although it's just itself one game-based definition. And it turns out we can do that. So we will give a metric or definition called indistinguishability under chosen plain text attack, abbreviated IND-CPA. And here we'll give some intuition for it, and that actually captures a lot. If you kind of see the intuition, it's the games should be relatively simple. So effectively what the intuition says is the type of scenario we saw in the voting example is kind of the worst case. So what we do is imagine that the adversary knows that the sender is encrypting one of two messages. The values of these messages are public. The adversary happens to know them. They are strings of some common length. And the only unknown for the adversary is, was it this message that was encrypted or was it this one? And we challenge the adversary to figure it out. What it has to help it is that you give it the ciphertext. This has been computed under a key that the adversary doesn't know, but it's provided with that encryption coming either from here or here. And then you ask it, well, which was it? Did I encrypt M0 or did I encrypt M1? And if it figures that out, you declare the scheme to be bad, and if it doesn't, you declare it to be good. So that's the basic idea. Now we sort of slowly even strengthen it. Strengthen it means we give the adversary even more capabilities. For one thing, these messages are not just known to it, we'll let it even choose them. If there are two particular values for these messages which surface some kind of weakness in the design, then it gets to pick and point to those as the ones to be encrypted. The second thing we do is that we allow it multiple attempts. So not only can it see the encryption of one message, either this or this, but there'll be a whole sequence here and a whole sequence here. And we'll encrypt either all of these or all of these. Notice that the choice doesn't flip-flop. It's either this entire sequence or this entire sequence. Q is the number of messages, and even that can vary depending on the adversary. So you see our adversary now is getting a stream of ciphertext, Q of them, across all these Q encryptions, and it has to figure out, was it the top stream that was encrypted or the bottom? Again, it gets to pick all the messages. So it gets to pick these two, but also these two, and so forth. And moreover, adaptively, in the sense that it can pick these two and see C1, then it gets to pick the next pair and see C2, and so on. So a very powerful kind of setting. Okay, yeah?
Do we also let it pick the random string at the front? Is that allowed to the adversary?
That is not. So if you do that, then things get insecure. So because effectively at that point the encryption is deterministic, because you know the randomness going into the encryption. Yeah, so crucially it does not do that. So the sender's computer is doing that. Okay, so now we'll turn this into our formal definition, and as usual, this game-based definition is kind of the core element of the chapter and of the study of encryption. So that's a core thing to understand. So we'll spend time on it and can also probe into it and ask questions and so forth. So what it does is it encapsulates our prior intuitive sense into games. We remember the setup. We are here going to fix a particular symmetric encryption scheme, which means that we know the three algorithms that comprise it as per the syntax of encryption. We've seen many examples, ECB, CBC, counter. It could be any of those, but it could also be something else. As with PRF security, there are two games, and this time we call them left and right. They both have an initialize, which runs this algorithm to get a key. And that key is stored inside the game and not given to the adversary. And it will be fixed for the duration of the game. What the games export is a procedure called left or right. And that takes as input not one message, but two. There is a restriction that they have the same length. When the adversary supplies these two messages, the game is going to encrypt one of them. The only difference between the left and right games is which of the two is chosen. In both cases, this encryption algorithm is run with this key, here on the left message, here on the right message. This algorithm is randomized. Its internal choices are reflected in this $ notation, and you get back a ciphertext. And that's passed over to the adversary. It can call this oracle multiple times, and then it'll collect a whole slew of these ciphertexts, and from that it'll make a prediction. And its job is to predict, do I think the left messages were being encrypted, or was it the right one? In other words, which game was I playing? If you want to map it back to an application, this is the key shared between sender and receiver. You can imagine that the sender is encrypting either M0 or M1, and the adversary doesn't know which, and is seeing ciphertext. But it has been strengthened to the point where the adversary can even pick the two messages. Okay, so now how are we going to see how well the adversary did? It will look at its ciphertext, and then it will output a bit. And its goal is to output a 1 in the right world and a 0 in the left world. In other words, to just predict the index here, 0 for left and 1 for right. So what it outputs is a random variable, and it'll have some probability of equaling 1. So we're interested in the value of that probability. Once we fixed a game, we can compute that. That means we have our adversary, we run it with the game, and we see, did it output a 1 or not? And that's an event, and it'll have some probability. We compute it in both games separately for the same adversary. We run it here, compute the probability, then run it here, compute the probability. And as with PRFs, we're not interested so much in the magnitudes of these individually, but in how far apart they are, which is this difference. And that's called the advantage. Here's where INDCPA, the name of the metric, appears. So as usual, if you see a problem involving this, you know you have to look at the games on this slide. This tells you it's about this scheme, and this tells you it's about this adversary strategy. And the advantage depends on all of them, and you just look at this difference. The bigger it is, the better the adversary is doing. The smaller it is, the worse it's doing. So its goal is to try to make this difference big. Okay, yeah?
So for these, like, this is kind of a class of games, right?
Well, there's two games, yeah. Oh, you mean a class, meaning every time you change SE, you do get a different game, yeah. Right, so it's parameterized by this, and that encryption algorithm is used here. So if you imagine every time you change this, something different happens in the game. Yeah.
Well, what's like the significance of there only being M0 and M1?
So this is the sort of, that reflects this intuition that the worst case for encryption, or the best case for the adversary, is that it's told there are only these two messages being encrypted. It's one of them, figure out which. It's true that that's, at the moment, it is intuition in the sense that I'm postulating, or it has been recognized, that that's the worst thing. And if you can get security in that setting, you get a whole slew of other properties. So we're just trying to say, all you have to do is tell which of the two messages was encrypted. You know the messages, you even pick them. Yeah?
So in this case, if the advantage value is 1 or minus 1, it means that it's not secure. Whether it is 0, it means you don't know which one, the left one and right one. So it means it is secure.
That's right. You do also have to think that it may not be 1 or 0, maybe something in between. So there's a spectrum, right? So for example, if it's 0.1, it's probably not very secure. If it's 10 to the minus 20, it's maybe fairly good. And the other thing is that usually we'll avoid negatives. So what I would expect is that if you're getting advantage of -1, you can always make it a 1, because all you have to do is flip the output bit. So as a convention, we'll avoid negatives.
So just off that, that advantage basically in English will equal the amount, the scale of which you can tell it's like one message versus the other.
Yeah. Okay. So anything more about this? Because again, this is effectively the central thing in the chapter. That's what we'll keep coming back to and using in one form or the other. Okay, so then some details about it. One is that you don't allow the adversary arbitrary queries. There's one restriction. Whenever it asks 2 messages here, these are strings, they must have the same length. That's because we don't expect encryption to hide the length. So if you write an adversary where the lengths are different, if you write it in PlayCrypt, the game will reject it. And if you write it in a quiz, your grader will reject it. So, so now let's, as usual, go to this interpretation element, which is that if your adversary has an advantage close to 1, you view that as a successful adversary and an indication that the scheme is not good, subject, of course, to this adversary having reasonable resources. And an advantage close to 0 means your adversary is not doing well. That doesn't necessarily mean the scheme is secure, because maybe there's a different adversary that does have an advantage close to 1, but at least it's resisting whatever attack you're trying to mount. If you want to assess security, you have to consider adversary resources, because if you give it enough running time and queries, it could do something like run exhaustive key search attacks. And so the way we understand what INDCP secure means is that this advantage is small, no matter what adversary you give, as long as the running time and number of queries it makes are within kind of practical limits. So we will often informally use this phrase in talking about schemes. And as you can see, it's not very precise, but it's expected to give you some intuition. Often we'll be showing insecurity. That means we'll take a scheme and we'll demonstrate it's not INDCP secure in a very convincing way. Namely, we'll give some adversary, which we specify in pseudocode, which is very efficient, little running time on queries, and yet it will have pretty much an advantage of 1 or close. Okay, so then for our first example, we're just going to go back to electronic codebook mode. So remember, that was the scheme which encrypted long messages in the most obvious way. It just said, take a block cipher, we'll call that normal font E, k-bit keys, n-bit blocks. And if you have a message, break it into blocks and let little m be the number of blocks, and just encipher each block with the block cipher individually under your key. That's the most natural thing you might want to do. The symmetric encryption scheme corresponding to that is called ECB. And again, remember that when you look at this equation like this, there's a script font E and a normal font E. And they are different things. This is the encryption algorithm of SE. This is your block cipher. And here they use the same key. So you can write ECB succinctly like this. So we already saw intuitively that this is insecure. We saw that if you ran it like in the voting application, data leaks in particular, you can figure out other people's votes. But now we want to formalize that. We have a definition. So the question is, can we design an actual adversary in pseudocode that plays these games and actually gets a very high advantage? So we know how E works. We go back to the games. We know now what this is. It's given by our formula here. E is a public algorithm, but we don't know the key as an attacker. And it's our job now to design the strategy for the attacker so that it tells the left and right worlds apart, right? So that's the question now. It's the kind of question you'll look at a lot. Now that you know how E works, can you think of a strategy? How would your job is to make queries, look at the answers, and decide if left or right was encrypted. So does that make sense? So any ideas then? Yeah?
For each of them, you make a string of like alternate string blocks. So they have this like alternating pattern. And then it's kind of naive since it isn't guaranteed, but you just look for the one that has the alternating pattern. That should be the one that's encrypted.
Yeah, that's good. I think the one I'll give is a little different, but that works. Yeah. Okay, so whenever you have to give an attack, it's a combination of a little bit of intuition and understanding of the models. Once you understand the models, you still have to look at the scheme and figure out what's the weakness. There's no recipe to do that. There's no something saying, here's how you figure out what the weakness is, right? You have to invent that. But here in this case, we know, because we already looked at it, that intuitively, the problem is simply that it's deterministic, and that's going to be enough to break it. So you know that if you have twice encrypted the same message, you'll see the same ciphertext. Well, in IND-CPA, that's a problem. And here's the adversary that shows it. So what it does is it's actually going to query LR twice. Now the way Max did it, he did only once, which is a little more nifty. But I'm going to do it kind of the slow way, which is that I will query LR 2 times. Remember that each time you have to give 2 messages. So what's the intuition? You know that both times either the left is encrypted or both times the right. And what I'm going to do is in the left world have different messages, and in the right world have the same message. The values of the messages don't particularly matter. What matters is this equals this, and this does not equal this. So now what happens? Well, given that the scheme is deterministic, the expectation is that in the right world, both of these ciphertexts will be the same, because they depend only on the key, which is fixed, and on the message. But in the left world, for the same reason, they will not be the same. So if they are the same, I should bet on the right world and otherwise on the left. So, okay, so now that's our strategy. So any thoughts about that? Makes sense? Okay. So now, once you have written down your strategy, you will go through the steps of actually showing it works by computing the advantage. That is much more mechanical. Once you have the strategy, you just walk through the steps to compute the advantage. But it's important to do this because you may not have got this right. And if you didn't, you'll catch it. Besides the fact that in quizzes, you're asked to give this as a proof, it's actually a really good sanity check, because sometimes you may have made a mistake here and you can catch that when you do the analysis. So how do we get the advantage? We just go through the steps. We have to compute the probability of A outputting a 1 in the right world and then the left world. And we just do them one by one. So we take our A, that hasn't changed, and we look at the right world, which we see from the game definitions. Here we know that the way this oracle operates is to encrypt the right-hand side message. So now we look here and say, we know that these coming back will be encryptions of the right one. So both of them will encrypt zeros. And now we invoke the fact that the scheme is deterministic. And so when you encrypt the zeros twice, you get back exactly the same thing. And so this equality will be true, and so you'll return a 1. When you go to the left world, what's changed is that in this pair, the left thing is encrypted. Notice the adversary is identical. They didn't change, and the conditions under which it returns 1 and 0 also didn't change. So what changed is now this C1 is an encryption of 0, and C2 is an encryption of 1. So we're asking, will those be equal? And the claim is, not only will they not likely be equal, they'll actually never be equal. Why is that? Because E is a block cipher. So when you apply it to 0 or to 1, it'll give you back for sure different things, given that the key didn't change. And so this will never trigger, and so you'll always return a 0. So probably returning 1 is null. And then we subtract them, and we get our advantage. And we notice now that this A was very efficient, just 2 queries, kind of linear running time. So it's a very effective demonstration that this scheme is not IND-CPA secure. Yeah?
So the E in SE doesn't necessarily have to be a random thing?
You mean like this E?
No,
This one?
yeah.
This has been specifically defined by this formula. It's a very specific thing here. Whenever you have an encryption scheme, it will tell you how this algorithm works.
Saying that in this case it doesn't necessitate randomness. Previously when you
Oh, okay. Yeah. So in ECB, it's not randomized, and that's exactly why it has a weakness. Right? So if we tried this with some of the randomized schemes, this attack wouldn't work. Yeah.
So, like the randomized mean, like the previous things that, like the previous left game, there was some like picking a random encrypted message from the like F0. Like in this case, there is like union that is
Wait, which previous game?
like the like previous case for like you introduced the left and right.
Here?
Yeah. And when when we see the return.
Oh, you mean here?
Yeah.
Okay. So what this means is that this may be a randomized algorithm, and it says you're running it picking fresh randomness. But a deterministic algorithm is just a special case. So when you have a deterministic one, there's no randomness to pick. So this notation just means that C equals EK of M0, right? So it's just a generalization of an assignment statement. That's a good point, yeah. Okay. So this is a small generalization. It just says that just as we saw intuitively, you can generalize this to show that it doesn't matter how these encryption algorithm operates, as long as it is deterministic, attacks like this will work. And here's another one, but I think it's the same or similar to the homework, so you'll be playing with it anyway. Okay, so as you asked over there, this IND-CPA game is quite specific. It's saying, well, you pick these 2 messages and you encrypt one, and it's natural to say, well, but why is that the right metric? What we were after is to hide every possible information about the plain text, and why would this funny game do it? So it turns out that people have investigated that, and how you can get some idea is to think about other properties you want. For example, when a sequence of encryptions have been done, could the adversary get the first message? We also talked about could it get a bit of one of the messages and other things. And we want all of these things to be hard. And at first, it doesn't seem like IND-CPA addresses that, but it turns out that it does, because if the scheme has this property, all of these properties are consequences. So you can prove this mathematically, but if you give me a way to recover a message, I can use that to violate IND-CPA and contradict this type of security. And once you've looked at enough of these, you start understanding and believing that this really is a good metric, because everything else you want is a consequence. So we won't prove that here. I do that, let's say, in a grad class or something, but it's good to know. Okay, so now that we know how to measure security, we're going to be going back to these randomized schemes. Remember, we introduced them exactly because they circumvented weaknesses in ECB, and they look pretty good. And now we'd like to validate that feeling and say that we know how we want to measure security, let's test them out. So let's first go back to counter mode. It's a simpler one, and take another look at it. So remember, the setup is we had a function family, not necessarily a block cipher, so it needn't be invertible. Let's say k bits keys, n bit inputs, and some possibly other value for the output length. And we had defined what the counter mode scheme was based on that. If you remember how it worked, this shows you the special case that the messages have just one block. One block means they're one L bit string. When you run the encryption algorithm with some key on a message, it will pick this C0 value at random and add 1, run the function family with the key, get a pad, add the message to that, and that will be the second block of the ciphertext. So your ciphertext is 2 blocks long, the first random and the second created like this. So I'm now interested in evaluating IND-CPA, and what we're going to observe here is that even from that point of view, there are some weaknesses in the sense that we will find a non-trivial attack. This attack won't be damaging enough to make applications fail in practices if the values of n and l are big enough, but in some cases like triple DES, it actually does create problems. So here I'm going to give the idea of this attack, which actually again exploits the birthday problem. It's going to consider that 2 messages, each 1 block long, are encrypted, and imagine that the adversary is trying to figure out whether they're equal or not. So a priori, the randomization prevents that, but that is only true if certain bad things don't happen. So what's bad for us, or what's called lucky for the adversary, is that in these 2 encryptions, both of these random choices for some reason end up being equal. It's not very likely, but these are n-bit strings, and there is some probability that if you pick 2 n-bit strings, you will get the same ones. So what our adversary is going to do is hope for that to happen. It will submit these 2 messages. If they're not equal, it will shrug, but if they are equal, then it gets happy. And the reason is that now it can figure out whether M0 equals M1. Why is that? Because it observes that the equality of these 2 blocks here exactly tells it that. Why is that? Because if this equals this, then P1 and P0 are the same. So C01 and C11 are the same exactly when M0 and M1 are the same. So this collision ended up being a way to violate security. So that's the base observation. Now, by itself, this doesn't do much, because as long as this is big enough, say 64 bits, well, this only happens with probably 1 and 2 to the 64, this equality, so why is it a problem? But that's where the birthday attack comes in. The birthday phenomenon says that once I start encrypting somewhat more than a few messages, the chances of this type of collision are going up quadratically, and that starts getting exploitable. So that's what our attack will actually do. In order to write it down, I'll first just recall things. We've said these things before, but we like to use and leverage these data structures. This has nothing to do with cryptography, but if I have a list, let's say, of n-bit strings, I'm interested in a collision in that list. That means a pair of indexes which are different, but the corresponding strings are the same. And as a sort of CSE 101 problem, I could ask you, I give you a list of strings, please write an algorithm that will determine if there's a collision or not, and if so, return the corresponding AB. And as a default, your algorithm is supposed to return 0, 0 to say, sorry, there just wasn't a collision. So you know the techniques from algorithms, and it turns out there are many ways to do this in about this much time. To me, the simplest is you sort the list, which takes q log q comparisons of these strings, and each comparison takes order n time, and then check whether any two adjacent things are equal. But in any case, we'll just assume such an algorithm. It's called find list collision. And you can also use this in your quizzes if you need to write. You can just invoke this algorithm. And so with that, so here's the Bertie attack on counter mode. So it's going to have a parameter q, which is the number of queries it makes, and intuitively it's the number of messages the sender encrypted. And it's going to hope that it gets lucky in the way we saw. And once it gets lucky, it'll exploit exactly the weakness we saw. So here's what the details are like. As usual, our adversary is pseudocode. Remember, it's playing formally the left or right IND-CPA games. So we expect that it'll call its left or right oracle, and eventually it'll return a bit, trying to say if it was in the 0 or the 1 worlds. So the strategy for our adversary is that it's hoping eventually to be able to test equality of encrypted messages or have that information leak. So what it does is, in the left world, it makes sure that all the messages submitted are different. And in the right world, it makes sure that all the messages submitted are the same. Now, in the details, remember that these messages in this case, as per counter mode, need to be strings of length L, at least if they're 1 block long. So I'll let this denote the integer I as an L-bit string. So L zeros is a 0, etc. And so here I just put 0. So that's the all 0 string. But here I put 1, 2, 3, 4, 5, etc., changing in every query. And I do this q times, where q is some parameter. When we get back ciphertext, the first thing to know is that they're coming back from counter mode, and that tells us that they will have 2 blocks. Every ciphertext will have 2 blocks, a 0th and a 1, and we know that this block was chosen at random, and this one was computed by this formula over here. But whereas that picture had 2 things, this is now happening q times. So we do have to keep track of a fair amount of stuff. There are q encryptions and hence q ciphertexts, and each ciphertext has 2 blocks. Okay, this lucky event concerns the first blocks. So what I'm going to do here is test for that event among now all the q blocks I got back for the first block. So I look at all the first blocks, and I ask my find list collision algorithm, can you find 2 of them that are the same? Maybe it'll say, sorry, you didn't get lucky, there are no 2 are the same. In that case, I return a 0. But suppose it says, no, there are 2 that are the same, and they're the pair A and B. At that point, I'm in the position shown here. So what I do is I look at the corresponding right blocks, the other blocks, and test them for equality. And that's my guess. So at this point, I go back to these queries. I index into the Ath and Bth ciphertexts. And I look at the first blocks, this and this, and I test for equality. If they're equal, I say, I believe I'm in the right world, and if they're not, in the left world. And that's it. So that's the rendition of the attack. And you can figure out its running time quite easily, exploiting what we know about FLC. So we'll go through some details of how to handle, yeah?
Why do you stipulate that A and B can't be 0? Or like 0 to the L?
That which can't be 0 to the L?
A and B, right?
Oh, that they should not be 0?
Yeah.
Well, if they are 0, it means that this list had no collisions. So at that point, I don't know what to do. My adversary feels a little stuck. So it just decides to return a 0. Basically gives up. Okay, anything else? Okay, so then we'll step through the analysis. So the slide looks pretty busy. It may be a little scary until you realize that most of it is just repetition. So here I've just copied the adversary from the prior page, nothing new. And here I've just copied down the right game. Nothing new except to make it more useful. It's been specialized to counter mode and furthermore specialized to one block messages. So here's initialize, you pick your key, and what left or right does is if you give it 2 blocks, it starts doing counter mode. That means it picks a random initial vector, then it runs the family of functions with this key on this +1. Remember what that means is you add 1 as an integer and go back to binary to get a pad value. And the second block of the ciphertext is just the pad value plus your message block. Right? If there were more message blocks, of course, you would be doing this more, but this is the special case of M0 and M1 being 1 block long. So now we know exactly how LR works, and the fact that we are in the right world is reflected in this being M1 and not M0. So now we can go to the adversary and try it out. So what are we interested in? Does it output 1 or not? So we look at the code and we say, okay, if what's coming back AB is 0, 0, it certainly won't output 1. So we're interested in the case that it's not 0, 0. In that case, what the adversary does is index into the Ath and Bth ciphertext and look at their second blocks and compare them. So let's see what happens. So we know how this is computed because it's given by this formula in this game. So we know that it'll take the message, which here will be the right message, and then it'll add P, which is given by this formula. So it'll look like this. Remember that here we're looking at the Ath ciphertext, so this C becomes a C sub A. For C sub B, it's no different. The formula is the same. It's coming again from this game over here, and again we're using the right message, which is appearing over here, and this 1 is coming from here, and so forth. So that tells us the values of these 2 ciphertexts. So now they're being compared here, so let's compare them. To do the comparison, what we note is that this here and this here are actually equal. So why is that? Because that's exactly what this AB not being 0, 0 means. It means I found a collision at points A and B in this list, so these 2 are the same. But if that's the case, these whole expressions are the same, so these 2 things are the same, and so our adversary will indeed return 1. Now that was true as long as this AB pair was not 0, 0. So what we've actually argued is that if this happens, the adversary is sure to return 1. So its overall probability of returning 1 is just the probability that there is a collision in the list. So now we have to estimate that. And what we notice is that these C values are chosen here. And that means they're just random n-bit strings independently chosen every time, and there's q of them. So the chance of a collision, 2 of them are the same, is our collision probability formula for throwing q balls into 2 to the n bins. Why 2 to the n? That's the size of this space. And so we end up with this probability. Okay, so there's quite a lot of different steps there, and a good exercise here is to walk through them. So you slowly go through every step and understand why it all works out. But no individual step is actually difficult. It's just a question of a lot of them. Yeah?
So LR always returns the encrypted output of something. It just, what's changing in whether it's the right game or the left game is which one of the messages is the input to that corresponding output.
Yeah. And in this case, I'm looking at the right game, so it's always M1. That's true for all the queries made here. This choice is random and independent at every call to LR. And if you were in the left game, it's completely different. New random independent choices there. It has nothing to do with these. Okay, we go through the same exercise for the left game, and not much changes. Same adversary. The change in the game is 1 bit. The M1 here became an M0. So almost no changes to what's written, and not much change to the analysis either. So we're again interested in the probability of outputting 1. So we again need to look at when AB is not 0, 0, and see whether CA1 and CB1 are the same. We know the formulas for them. How? From here. So it says that CA1 is E of k and CA0 here plus M0. What would M0 be? Well, it's the value of it coming out of here. If you're looking at A, that means I is equal to A. So here we get A, and here we get this enciphering. And on the other side, you get B and the corresponding enciphering. Now again, you know that these two are equal because AB is a collision. So if these two are equal, then the outputs of E sub k are also equal. But A and B are not equal. We made sure of that here. They're counter values. So in fact, these will not equal each other. And so our adversary will never output 1. Yeah?
So is it a convention that the left game and the right game will both have the name LR?
So the name of the procedure is the same in both games, exactly because your adversary has to call it and it shouldn't know which game it's playing. But the way it works is different, right? It's implemented differently, but the interface name is the same. That's the same as in PRF, right? It was called FN, but it worked differently in the real and random games.
So like say in a test, would we have to like specify like both of the procedures using M0 and M1?
So you mean these?
Yeah, like, yeah.
So the games are given, right? So the games are always fixed and given. And they're general. So we had the general formula for games, right? So they're always these games. What I did to make things easier is I just expanded what E does and wrote the details.
Oh, actually, okay.
Right? So that's not something, I mean, you will not, if you get a problem referring to IND-CPA, you don't invent games, they're the ones that are known. Okay, so now the final advantage, that's simple. We just subtract the two things we discovered. Is the collision probability then minus 0. And we can use our fact, which lower bounds this at about 30%. And here comes this parameter q, the number of queries our adversary made. And this gives you about q squared divided by 2 to the power the input length of our function family. And now we start getting interesting conclusions. We see that if we set the number of encryption queries to 2 to the power half of the input length of the function family, you get a pretty sizable advantage. Now, 30% is, from a security perspective, sizable, right? You don't really want adversaries to be breaking your schemes with 30% probability. So this is considered high. And so now we have an interesting conclusion, which is that if you run counter mode encryption and you use an underlying function family with n-bit inputs and l-bit outputs, then there is an attack using 2 to the power n over 2 queries. And working through all our formulas, we can even estimate the running time, but the main element of the running time is that it's also on the magnitude of this Q, because this very much dominates this stuff. And this is always true. It doesn't matter how well you build this E, but this attack will always exist. Okay, so we now have some conclusion. And if you didn't understand all the details of this at this point, it's fine. Just go back through it later and kind of slowly go through it, and hopefully it'll work out. So that in particular is what gave us, for example, this, which I've showed you before, but these were the attacks on triple DES, which broke TLS encryption and which resulted in triple DES to be withdrawn. And it's exactly the attack we showed. So they get a little more data out of it, but they do it for CBC, but it's basically the same thing. So that tells you that this stuff comes up. Okay. So if we had some kind of attack on counter mode, it might start getting a little scary, because generally I've already said that counter mode is exactly what everyone is using, and yet we're saying we just found an attack on it. So what's going on? Well, the thing is that our attack has this kind of advantage. The number of queries, or the number of messages encrypted, divided by about 2 to the power the input length of the function family, or if you're using a block cipher, the block length. But if you make n big enough, for example 128, we're actually okay with this. So this isn't yet a problem, but it would be a problem if there's a better attack. If somehow there was one that had success probability q to the 4th or something like that, it would be in a much worse position. So how can we possibly determine if we have found the best attack yet? And that's where some of the theory in cryptography comes back to deliver a rather sort of surprising but useful message. It effectively says that there isn't a better attack, that this is the best possible. So of course that statement has some qualifications, and you have to understand the technical conditions. But as a high-level conclusion, it's pretty nice, because it's the first time we're seeing something where you can look at a scheme and say, this scheme actually works. So in a little more detail, there are proofs which say that if you consider an arbitrary adversary making Q queries to its LR oracle, then its chance of distinguishing, or its advantage, will not be more than this. And here you have a formula, and it depends on the number of queries the adversary made, but also on the total number of message blocks across all those queries. So remember, the queries can have different lengths. Each is a pair of messages, and the lengths of them across different queries can vary. And here you sum all those up. And what this says is, which is very novel for what we've seen so far, is that it's not possible to do better than this. Yes, I will give up this much advantage, but I can be sure that no adversary will get an advantage even higher than that. And then if I make my little n here big enough, then hopefully this is quite small. So that's kind of the conclusion. Now remember again that this is for counter mode. It's not saying this is true for an arbitrary scheme, obviously not, because many schemes don't work at all, but for counter mode it's true. So as an example, if you consider adversaries that only query one block messages, then the sum of the lengths of the messages is just the number of messages. And then the formula looks like this. And now you see that it's very close to this. So it's in that sense that it's telling you that you can't really do much better than that. If we consider that most often the family of functions is AES, then this little n is 128. And so that says that this value hits 1 around when q is 2 to the power 64. And that's how AES-based counter mode is understood in practice today. So they see it as being something with which you can encrypt about 2 to the 64 blocks, and then you have to start changing the key. Okay, so now what I'm going to do is state a formal theorem that captures the claim I've just made. And the purpose of this again is because these kinds of results are in fact one of the most important takeaways in terms of understanding and evaluating cryptography. And in this class we don't prove these, I do that in the grad class. But not only are they important to know in terms of picking and understanding schemes in practice, but you can get questions in quizzes and exams which leverage that you understand what this statement means, that you can interpret it. And so what I'll do now is tell you the statement and how to interpret it. So we are considering counter mode, and the way we fix it is we first fix a family of functions. So for example, AES or anything else, and we have with it our key length, input length, and output length. Once we've fixed it, counter mode gets defined by the formulas that we've given, and we know how it works. It picks this random initial point, then it starts incrementing the counter, applying E, etc., etc. So whatever it is, we know now what this symmetric encryption scheme is. Now I want to consider some arbitrary adversary who's trying to violate IND-CPA, and it will have some advantage. Of course, this advantage will depend on how much running time it had and how many queries it made to its left or right oracle. We would assume that if these numbers are bigger, it's going to do better. But nonetheless, I want to somehow limit this advantage, or say it's not too big. I will also, as in the previous slide, be interested in the sum of the number of blocks across all its LR queries. So now our conclusion roughly here is the theorem is saying this cannot exceed this number here that we saw from the last slide. It's saying that yes, this may grow with Q, but it will not go more than this. And that's a powerful security conclusion. However, this theorem brings in something new that we didn't see before, and in retrospect is a little natural. Counter mode is using AES or whatever E we have here. If whatever we're using here is a weak object, you can't hope that counter mode will be good. If this is like doing some silly thing like being the identity function, obviously this is going to fail. So this theorem has to somehow reflect that I'm assuming E is good. And the way it does that is here by saying that I put here a term corresponding to our ability to violate PRF security of E. An interesting element of this theorem is it's now talking about PRF security of this family of functions and effectively using that as an assumption on E to show security, IND-CPA security of counter mode. It shows up here as the advantage of some other adversary that the theorem constructs based on A. So the statement then says, given an adversary A, I will give you back another one B such that this formula is true. Okay, so now how do you interpret this? Well, if you consider adversaries with reasonable resources, then meaning you've allowed a number of queries and their lengths to be small enough, then this term is small, or at least you can limit our usage to cases where this term is small. Now, if we assume that E has PRF security, it means this term is small too. Hence, so is their sum, and so this is small, and that means SC is IND-CPA secure. So in that sense, the theorem is saying if E is PRF secure, then SC is IND-CPA secure. And so that's kind of the high-level conclusion. Okay, so this is quite a novel kind of object, and we'll see a few more, and hopefully you get used to them. But if there's any thoughts now, then you can also go into them. Yeah?
Yeah, like I know the proof is really big, but how can you prove that there's no better adversary, right? Like this boundary, because like haven't there been cases that I see in cryptography where like, oh, this algorithm is secure, and then there comes an adversary that like kind of beats it, right? Has that been like a phenomenon? So then
So once you have the proof, and assuming the proof is correct, then what it's saying is that you will not find such an adversary A having a better than this advantage unless the PRF security of this E fails. So in other words, if you're using AES, if someone actually finds an AES attack in the PRF sense, then yeah, then you're sunk. And that's an assumption I'm making here, that there is no such attack.
I understand like what the formula is saying. I just, for me, is how do you prove that this formula is the other.
Okay, but then basically you're asking for the grad course, right? So, but roughly speaking, the way it works is it breaks into two cases. So if you remember the PRF definition, there was a real and random world. So what you say is that the real world corresponds to real counter mode, but except this, with this much of a loss and advantage, we can pretend we're in the random world. When we're in the random world, I can give a purely probabilistic analysis that says your adversary will not have advantage better than this. Purely combinatorial probabilistic analysis. And that's how it goes. Yeah?
So we make the assumption that your security of E is good.
Yeah.
Is that, I remember like when we showed that CES was thought to be secure and it was working. Does that mean like we can't really prove for a cipher itself for the nature of the encryption?
That's right, exactly. So we don't at the moment particularly have ways to prove these kind of things for the cipher. And so here, that's where this theorem is making an assumption. And at the moment, we have no way around that part. So the purpose of the theorem is to say, at least your assumptions stop there. It doesn't go to the next stage. Okay. So, okay, so I actually did have a little bit of intuition, maybe just but the way we look at it is to take our adversary and consider it making all these queries, and let's say m is the number of blocks in a query, and look at the ciphertexts that come back, and we'll let C sub I be the one coming back from the ith query, and it'll have m plus 1 blocks, the initial random choice and the others computed by counter mode. And then we will look at how counter mode works, and remember that we know how those ciphertexts are computed through this kind of formula. And then we'll take an imaginative step. We'll say that instead of using the block cipher with the key over here, we'll use a random function, a purely mathematical object is in our game that every time you call it returns random stuff. This is a thought experiment because you can't implement this efficiently. It's way too big. But within that thought experiment, we can still ask if the scheme is secure, whether what is the advantage of this adversary. If we can figure that out, the PRF assumption on E says we're done up to the advantage of violating PRF security of E. So we come down to this thought experiment question, and I don't think it's worth going through all the details, but effectively the only problem would arise when there's collisions across the values on which the function is being called. So once we've bounded away the probability of that, we have effectively perfect encryption, and our adversary will have no advantage. So that was just I mean, I don't expect people to totally get the intuition. This is going a bit over the syllabus. So just to wrap up all this stuff, this says that the cipher block chaining scheme has a very analogous result. We don't have to go through this one in detail, but all it's doing is it's saying instead of counter mode, I can substitute CBC, and everything is the same up to some small changes in exactly what the formulas are. But the conclusion is cipher block chaining is also a good scheme from the point of view of having proofs. So some of the ways you might exercise how you understand this come here. This is not a technical thing. It's something like imagine you're having a conversation with someone who doesn't know that much crypto and needs to pick an encryption scheme, and they want one based on AES, and they tell you, which one should I pick? Well, what would you tell them? How would you explain to them what is a good choice and what isn't, and why? And if you try to have that conversation with someone, you will find that you leverage the things here and probably have gained a good high-level understanding. Okay, so I can switch then to the my weird random topic things and talk about something else. So assuming that's okay. Okay. So here I wanted to tackle something that's actually kind of a, maybe a delicate question that comes up in education, and just try to give some perspectives on this. And you may or may not agree, and you can tell me what you think. But often what students will do when faced with a problem, like finding an adversary in this class or something like that, is ask, well, what's the approach I should use? And what steps should I follow to reach a goal? And while in some cases, or for some types of problems in some places, that's possible, as you go on, and in particular for problems here, there isn't really a complete answer. There is no sequence of steps I can tell you of the form, do this, 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 and this, and you are sure to solve the problem. There's always going to be something where you need a little ingenuity. And part of the challenge, but I think also part of the interest, is that you have to figure this out. And part of the reason it's left to you is that everyone actually figures it out differently. No two people have the same intuition, the same approach, and everyone finds their different way. And I think that's actually what education is supposed to encourage you to do. It's not supposed to tell you the exact sequence of steps, but to encourage you to see how you would think about it, so you can then come up with that sequence of steps. So I don't know if that's how people see it, but I wanted then to further that by talking about an analogy. And this is a well-known sort of metaphor. You remember that you can lead a horse to the water, but you cannot make it drink, right? It does that on its own. So what's the analogy here? Well, what if the horse, came within a foot of the water and then said, tell me what to do. How many inches should I open my mouth? How should I move my tongue? Well, what are you supposed to tell it? I would be really stuck with questions like that. I have no idea how to answer them. So that sort of that doesn't work. And there is a limit to how far someone can take you, is the lesson from that. So in that sense, what I suggest is you see the purpose of teaching and classes to lead you to the water, and imagine that the rest is your job. You're going to go the rest of the distance on your own. And it's a fun journey, right? You're going to figure out how to do this. It's not merely that it's fun and a challenge, but it's actually very difficult for an instructor to tell you how to take those steps, because every person does it differently, and there is no single answer. So it's a good sort of perspective to get when you're working on problems, to think, okay, where am I in this? Have I got to the point where the rest is up to me, or is there still something someone can help me with? And you will find that once you see yourself as being in that position, you will find your own way, and you'll find different ways. Everyone will have a different way of figuring out how to actually drink the water. And you will start discovering things about yourself and discovering your own strengths at problem solving. So my belief here is that if you think about what happens with the horse, why does it work, right? Why is it the case that you can put it there and it'll drink? It's because it has an ability, an innate ability to drink. Nature has already told it how to do that. But if you try to push it too much and tell it what to do, it'll almost forget what it knows. If you leave it to itself, however, it will kind of discover all that by itself, right? And so that's what I believe is true also for students and for you. You have in you an innate ability to solve problems. You have in you an innate ability to be creative, but it has to be found, and it's not going to be found if someone is constantly giving you answers. So, but once you're in a position where you know it's my step, you will start finding it for yourself. Okay. Okay. So then I'll take that a little further. You can ask, what is the purpose of teaching? Well, many people's understanding of teaching or of an instructor is they're supposed to tell you how to do things or give you some facts or something. And I would put it like this. What a purpose of a teacher is to get you to the point where you don't need the teacher anymore. You can just tell the teacher, thanks, your job is done, I'm good. Okay, and that's a good teaching. Okay, because it's not about constantly needing that. It's that you've reached the point where you can just say to the teacher, okay, thanks, bye. Okay, and that's it. So just like imagine what happens with the horse, it'll happen slowly. You can imagine the horse the first time brought to within 6 inches of the water. The next time it stops at a foot. And after a while it tells the person, 10 feet from the water, hey, it's fine, you go sit down, I know how to do the rest. And eventually the person is not even needed anymore. Right? So that's again the analogy. Okay, so any thoughts about that? Or is it weird or, yeah?
I agree with this teaching style and sentiment. However, the problem is like, you need to give students like scaffolding and structure in certain ways, because like, let's say, using an analogy of like a person learning, right? Let's say you have a baby, right? And babies are very good at picking up like learning based on their environment. But if you give them continual random environments, right, and they have no structure, right, they have no way to like forward propagate and back propagate learning, it kind of evaporates. They're saying when like, let's say like I don't like math classes where they'll give you like this one like they give you the implementation, you just repeat the implementation over and over and over. But at the same time, if there's no idea on no structure whatsoever on how to achieve your solution, it becomes very hard, right? So I think it's just finding the balance between.
Yeah, absolutely, totally right. So, and I try to find the balance, and you do too, and we work on that. So that's totally true. No arguments. Yeah.
I think one of the more unfortunate things about our generation is that like we have like the resource to like tell us how to drink water like always readily available. I feel like we're kind of inclined to like just take that easy way instead of like before where you would have to like maybe go through like a textbook or like yeah.
That's a very interesting proposition. I think we could spend a whole class exploring that. That's very interesting. I mean, I'd like to understand, for example, what makes this generation really different in that way. Is it the internet or what? Yeah, it's the internet. Uh-huh.
Or and ChatGPT, like so let's say AI tools. But I think that's also like the reason why people are more dependent on AI for help is that as schedule and free time becomes more and more abbreviated, you're more inclined to use tools to like finish your work fast, right?
Yeah.
It's just that people learning often comes at the expense of like a fast outcome. And I think that isn't even like a personal like your morals aren't aligned thing. We just
You need to get stuff done
yeah,
in a certain time frame.
And I think that's a real problem.
Yeah. So there's a second part of this talk where I go into things like more motivations for this. But I think one of the things that would come up there for me is that you sort of want to enjoy this process. And so even if you could use an AI, it's just more fun not to. And once you're there, things change a little. Of course, as Max said, it's true that if you're in a tight situation, you have to do something in a deadline, you have a quiz. I mean, it's hard, right? But if at some broad level you see things as enjoyment, I think it helps. Okay? More thoughts? No? Okay, and we'll stop 5 minutes early. We finished the chapter, so good point to stop. Oh, by the way, the quiz, I put up, where is it? So I put up information and practice for the quiz. So that'll have information like, location and logistics, what you can bring and not bring, and a slew of practice problems. I hope this is the scaffolding you're looking for. But it tells you there's a lot of practice problems, and you can try them out. And yeah.
And then how many questions would the quiz be? Like the size of homework, or? Not like but these questions aren't like you can breeze through in a second. That's why I've asked.
Yeah.
About the
Yeah.
Okay.
So.
Is the quiz based on computer, or like do I have to write down it?
The quiz itself, you'll write on the quiz itself. So it's not computer based, yeah. There's also more problems in the slides. I'll go over this next time more, but I just want to alert you it's there.